Okay. And the last rule that we're looking at here is when you're dealing with a polyatomic ion, the oxidation numbers for all of the elements in the polyatomic ion need to add up to the charge on that polyatomic ion. So for example, SO4 has to add up all of these to -2. So oxygen is -2, but there are 4 of them, right? So in total, oxygen we have a total of -8, which would mean sulfur, we have to figure out, well, what would sulfur have to be for sulfur plus these 4 oxygens to add up to -2? So in this case, it would be +6. So you have +6, 4 -2s, right? So +6 and -8 add up to -2. So over here, we have a dichromate ion. So again, oxygen is -2. So there are 7 of them. So that's -14. But you have to consider, okay, well, what does this value here, remember there are 2 chromiums, what does this value have to be for this to be +12? Because remember, we need this to be +12 and -14 to add up to -2. So in this case, it would have to be +6 again. So +6, +6, 7 -2s all add up to -2. So you're using, it's kind of like you're using algebra, simple algebra of what would have to be added to this to get it to be -2 in that particular case. Right? And that goes for any polyatomic ion, right? So even, let's do, we already did that guy. Let's do phosphate, right? So phosphate is PO4 -3. Oxygen's -2, so there's 4 of them, which would give us -8, right? And then you have to think, well, what would have to be added to give this overall -3? It'd have to be +5. So phosphorus would be +5 in this case. So you're assigning it on an element basis, but you do have to consider how many of each element you have to make sure it adds up to that overall charge. Okay, so this is from your textbook. It's just a summary chart looking at the different rules that we had already discussed. Okay, so let's look at redox reactions. We'll get back to those oxidation numbers because we're going to put them in action in a second here. So remember, redox is short for reduction oxidation reactions. So when you're looking at a redox reaction, how you actually know that you have one of them is you have to look at the oxidation numbers for the elements in the reaction. So there should be a change in those numbers. Oxidation reactions is when there is an increase in oxidation numbers. So let's say you had -2 to start, and then at the end of the reaction, the element is now +1. So the oxidation number has gone up. So that means that that process of going up in numbers is called an oxidation reaction. A reduction reaction is where the numbers are going down. Okay, so this maybe is the opposite. We went from +1 down to -2. The number is decreasing. So oxidation numbers is where there is a losing of electrons. Pardon me, I don't want to do that yet. So oxidation numbers, right, is where you have electrons being lost. Reduction reactions is where you have a gain in electrons. You have to think, it's becoming more negative. There's going to be extra electrons than there were previously. Oxidation reactions are becoming more positive. They're increasing, which means they are losing electrons. Okay, so here we have a reaction, and we're going to practice our assigning oxidation number skills here. So the first thing we're going to do is we're going to assign every element that is in this reaction an oxidation number. Okay, so here we have chlorine and 3 oxygens, and this is a polyatomic ion. So we're going to assign, remember we're assigning for each element. Okay, now coefficients mean nothing, okay, when we are assigning numbers. Coefficients are going to come later on, so the next lesson will be, well, how do we balance these reactions? Because there's a little bit of a different approach. For now, we're literally just looking at the oxidation numbers and what changes are happening here. So oxygen is -2. There are 3 of them, which gives us -6. And we have to have this add up to -1, right? So that means our chlorine is +5, right? So 5, -6 is -1. Now iodine here, even though this is not in its elemental form, this iodine has to add up to 0 because it's a neutral structure. So what I mean by that is iodine would typically be a gas. Actually, pardon me, it's going to be a solid in its elemental form. But in this case, it has to add up to 0 anyways. So the only way for this to be a possibility is for each one of those iodines to be a 0 regardless. Okay? Chlorine is a simple ion, so meaning it's not a polyatomic ion. So the oxidation number is equal to the charge, which is -1. Over here, we have a polyatomic ion, -2 for oxygen. There are 3 of them, so that's -6, which means our iodine has to be +5 for that to add up to -1 overall. Okay, so now, how are we going to know what is happening? We're going to look for a change in these numbers. So chlorine is going from +5 to -1. So it went from +5, ooh, I didn't realize I was going to do that. But anyways, +5 to -1. So meaning it's going down in oxidation numbers. So chlorine is actually the substance that is doing reduction. It is, in fact, this is gaining electrons. We're going from +5 down to -1. Oxygen is staying the same. So notice oxygen is -2, -2. There's no change there. You are going to have sometimes elements that are not changing, and that's fine. Those elements are just there because they happen to be part of the ions or part of the molecules that are involved. But if you look at iodine, iodine is going from 0 to +5, right? 0 to +5. So meaning what's going on there is iodine is increasing in oxidation numbers, right? 0 to +5. So iodine is actually the substance that is being oxidized or that is doing oxidation. If you have a proper redox reaction, there should be one element that is reducing, one element that is oxidizing. So you need something that is going down in numbers and something that is going up in numbers. So here's just a summary of what we had already looked at. Okay, so you can pause the video if you'd like now and try practicing to assign oxidation numbers for every element that is here. I want you to be aware though, this is an ionic compound, potassium permanganate, but this permanganate is a polyatomic ion. So just to kind of help you out, sometimes when you're looking at an ionic compound, it's easier to think of them as the separate ions, right? So we have potassium ions and permanganate. So that should help you. So pause the video, give that one a try. Okay, so let's take a look at the answers here. So we have the nickel and chlorine. So remember, you're assigning per element. So nickel and chlorine, this is a polyatomic ion. So these are just simple ions here. Nickel +2, chlorine -1. Hydrogen is in its elemental form, so it's just 0. And as I mentioned, it's sometimes easier to assign oxidation numbers if you write them out as the separate ions. Of course, this can only be done when you're looking at ionic compounds. So potassium is a simple ion, so it's equal to the ion charge. But permanganate is a polyatomic. So remember, the oxygen is -2. There are 4 of them, which is -8. which means that manganese has to be positive 7 in order for that total to be negative 1. Okay, so here is another practice. You can pause the video after we go through this to see if you get the right answer. So you're going to write out the balanced chemical equation with states, so if it's a solid, aqueous, whatever happens to be, for a single displacement of aluminum metal with a solution of copper 2 chloride. Okay, and after you write so this is, remember I mentioned that balancing can sometimes be different for redox reactions. In this case, this is just the regular method of balancing. So all of you at this point should be able to write out a single displacement reaction. So what the new part is once you've written out that balanced reaction, I want you to assign oxidation numbers for each type of element in every species. So for all the reactants and all the products. Okay, so here is hopefully what you have. So solid aluminum plus copper 2 chloride, it's a solution, right, which means AQ. We're going to have a single displacement, so aluminum chloride and then copper solid. So aluminum chloride, if you look at the solubility table, is aqueous. So for assigning, of course, then we balance accordingly. But remember, the balancing will not impact your oxidation states. So solid aluminum, 0, elemental form. Copper 2 chloride is a simple ionic compound. So we have copper positive 2, chlorine negative 1. Aluminum chloride, so again, this is a simple ionic compound. There's no polyatomic ions here. Positive 3 for the aluminum, negative 1 for the chlorine. And then solid copper is in its elemental form, right? So you didn't have to do this part, but just by looking at this on first glance, aluminum is going from 0 to positive 3, which means that aluminum is doing the oxidation reaction because it's going up in numbers. And copper is going from positive 2 to 0, which means it's doing the reduction portion of this reaction because it's going down in numbers. And chlorine is not changing at all. It just so happens to be there. All right, so try this out. Balanced chemical equation. Pause the video. Write in an oxidation number for each of the elements that are shown here. Okay, so hopefully you have 0. Right? Elemental form, hydrogen is also 0. Hydrogen, positive 1, chlorine, negative 1. Right? So hydrogen is always positive 1 unless it's a hydride or a hydrogen gas. And then, of course, for this to add up to 0, the chlorine had to be negative 1. Zinc chloride is an ionic compound, so it's just a simple, there's no polyatomic ions here. Okay, so this is, in fact, a redox reaction. So zinc is going from 0 to plus 2. So zinc is going to be oxidizing because it's going up in numbers. And hydrogen is going from positive 1 to 0. It's going down in numbers, which means it's being reduced. Now, when you're looking at a oxidation reduction reaction, we can also write this out in what's called a half reaction. Okay, so first of all, half reactions are always in reference to the net ionic equation. Okay, so remember what that means is we would have to get rid of our spectator ions. In this case, chlorine is a spectator. And you're only showing one portion of the reaction. So instead of showing redox together, we can write out oxidation on its own and then reduction on its own as two separate, what we call half reactions. Okay, and that's what we're going to look at here.